Hello there. As I walked over to the studio today, it felt the first hints of fall. College football and volleyball seasons are underway, and we had a great conversation on today's podcast. So life is good. So before we get into it, here's your reminder to like, subscribe, comment, send questions in, and we'll put the email address right down here. But this is not to get any kind of viewership, monetization, or money for the podcast. We don't make any money off the podcast, but what it does do is get this information out to as many people as possible. And we're an educational podcast, so we want to be visible. So anybody that wants to join the Price of Pain family can. So you directly can help us do that just by like, comment, subscribe, and send in questions. Any questions. It can be, what is computational modeling? Hey, how do you know when mice feel pain? Or, Josh, I think I'm subscribed to the YouTube channel, but I'm not really sure. How do I do that? All fair game. Okay, so my guest today is Dr. Chris McCurdy. He's a professor of medicinal chemistry, and he's the director of the University of Florida Translational Drug Development Corps. After listening to our conversation, you'll understand why he's also served as an advisor to the FDA. Yeah, that FDA, since 2017. Really knows his stuff. As a matter of fact, he's a leading expert in the research of kratom. But we don't really get into that today because there's so much groundwork to lay first. So he has the distinction of being the first guest to leave the studio with his next episode already on the books. We'll get to that after the WHO meets to discuss the worldwide use and potential regulation of kratom in November. But for now, why don't we go ahead and lay that groundwork for the discussion? And Kat, let's listen to some Ray Lynch.
Welcome to The Price of Pain, brought to you by the Pain Research and Intervention Center of Excellence at the University of Florida. Let's join host Dr. Joshua Crow in conversations with scientists, healthcare providers, and industry professionals as we delve into the highly subjective experience of pain and the ongoing effort to reveal its influence on our everyday lives.
And correct me if I'm wrong, the most recent research, and am I saying this right? Kratom?
Yeah.
Kratom.
Kratom.
Okay.
Kratom.
Oh, depends on where in the world you're from.
Depends where you're from, right?
Yeah. But you also have other work in cannabis and age-related cognitive impairment and cognitive decline.
Yeah, in collaboration with Dr. Setlow and in his group in psychiatry. Yeah, we've been doing work with that. And we have work on pain diagnostic that's in clinical trials. So that's a totally different non-opioid target. So
we've got plenty that we could talk about.
Yeah.
What's pain diagnostic?
It targets a sigma-1 protein. So it's a long history of receptors that were thought to originally be opioid receptors. And that's why they have a Greek nomenclature associated with them, like the mu opioid receptor. Mm-hmm. This one was found and named the sigma receptor. And over time, as we've got into the sort of genomic age, we now know that it's a unique protein, not even associated with opioid proteins.
Oh,
which is good, but it modulates several neurotransmitters. And so what happens is you can see if you block this receptor, you seem to be able to block chronic pain signaling. And so we thought that was really cool, but we started doing diagnostic tests in PET imaging with animals and collaborators at Stanford. And sure enough, we were able to start seeing some of the literature that was coming out around pain and this target. And we induced nerve damage in animals surgically, and then injected our compound as a PET imaging tracer. Mm-hmm. So it was radioactive, and then we could see this sort of increased concentration of that tracer right at the site of nerve damage. And so we've now learned that these receptors overexpress themselves at the site of nerve damage, and now we've moved from doing animal studies to human studies. We've scanned over 150 humans with a variety of different pain issues, and mostly things like sciatica, but we're looking at chronic regional pain syndrome and some of the other things that don't have good diagnostics for in the clinic. And this compound is very interesting. It really seems like it has promise to to identify what the physicians are calling pain originators.
Okay.
I say it's probably more like this is where the damage is, and by extension, you would say that's where the pain's coming from. And so we've been able to successfully impact a few patients that have been in chronic pain and now are not in chronic pain, just for manipulation that their physicians have been able to do based on the images that they've seen. So it's really interesting, but it also has what we call a theranostic property. So it's a diagnostic, but also therapeutic. Okay. And it has the ability, not at the concentrations or the doses that we use for the imaging, but at doses that we could do at higher levels, we can actually treat that chronic pain with very minimal side effects. So it's really cool.
So let's circle back a little bit to that, because there's a lot there, particularly for people who maybe aren't as familiar with neurophysiology and how nerves signal pain or nociception. And that's the other thing that I think we should probably get into a little bit, because on the podcast, we've had a number of pain researchers that look at chronic pain and differentiate that pain from any peripheral activity and really look within the brain at maybe pain modulation changes over time. So I think maybe the best place would be to start with the receptor. How does this receptor, you say that the receptors seem to collect at the point of nerve damage. So what's the role of the receptors to begin with? We're going to back way off here and start kind of at an elementary level.
So we're really still kind of unsure. And we do know that it's what's called a chaperone protein. So it's really not even technically what we would call a receptor now, but that terminology has stuck with it from the time it was identified back in the 70s till what we know now. As far as we've progressed, 50 years later, we can say, hey, this thing is not actually a receptor, but what it does is it interacts with several classes of compounds, including marketed medications, a lot of CNS medications. It's located deep within the cell and at the endoplasmic reticulum, so very specific structures right next to the mitochondria. And what happens is that the most of the time that receptor protein is just sitting there, not having any activity. But when there's a stress to the cell or some sort of insult to that cell, that protein can become activated, and what it does is it then moves from that deep intercellular store up to the cell surface, and it can modulate proteins like other receptors, G protein coupled receptors, or ion channels, or even transporters. And there's been a lot of work that shows that this protein can modulate many types of signaling. So even neurotransmitter signaling, ion influx or efflux out of the cell. So it can really serve as a point that influences what's going to happen to that cell due to that stress level. So we think it's there as maybe a check marker for causing that cell to die or causing that cell to repair itself and survive.
Interesting.
And so we really don't have a full understanding. And obviously the next jump from there would be, well, this must be a hot cancer target.
Right.
And it actually has been studied quite a bit in cancer. We did not particularly set out to look at it in cancer. We actually started out because of reports on its ability to modulate neurotransmitters, particularly those associated with psychostimulant abuse and activity like methamphetamine and cocaine. And our original funding in this area was to design and synthesize compounds targeted at treating cocaine use disorder and addiction. We did a lot of that work. It was really, really interesting.
So it seems, so there seems to be two different branches here. So if I'm getting this right, I'm trying to formulate an image here. And I went to this function just yesterday, as a matter of fact, a leadership function at the old president's mansion.
Oh, yeah.
And you walk up to
I forgot I was supposed to go to that.
No, you missed out. The food was great. But as you walk up, there's somebody inside. that meets you at the door and lets you in.
Right.
And that same person, as we were leaving, she walked over and did that. Kind of seems like, in a way, this protein functions the same way, almost like a butler, per se. So when it's time to let something inside or outside of the cell, specifically, this protein gets activated and moves to the door, essentially the channels that,
Right.
or the cell membrane, and then facilitates either chemicals leaving or molecules entering the cell that further elicit change. Is that first part kind of right?
That could be right. Okay. I mean, I don't think we know specifically exactly the movement and what causes it to actually move, how it moves to the door, if you will, and then what its interactions are once it's there at that sort of interface to the outside, right?
But you do notice that at least initially, and again, this is me trying to see if I'm understanding along to this point properly. It does seem that in a multitude of cells, this is not just nerve cells, correct?
That's correct. Okay.
So a multitude of cells, this protein exists somewhere inside the cell, and then something triggers it to move it to where it's found on the cell membrane, or interacting with the cell membrane.
Okay. And we know it exists pretty much everywhere in the body, which makes it even more challenging.
Sure.
Because if you're targeting a protein that's sort of ubiquitously expressed everywhere it can be, that means you're going to have a lot of non-specific signaling that shows up. And indeed, we see that particularly in metabolically active tissues, so in the liver, in the lungs, in the kidneys, in the heart, in the spleen, in the pancreas, in the brain. You see a lot of signal. And
just all the non-important stuff.
Yeah, all the non-important stuff.
Stuff that you don't use very often.
But and that's part of the problem with this as a true pain diagnostic, because yes, we can maybe start to look at differences in brain architecture between normal patients and patients that are in chronic pain and see if there are some differences noted there. We haven't gone into that sort of deep level of study yet. And the other problem is it seems to be very much active in the spinal cord.
Okay.
But we don't see it in the peripheral nervous system in healthy volunteers. And so when we see someone coming in with a complaint of sciatica or a knee injury or ankle injury, that area generally lights up pretty nicely with this diagnostic tool. And so what's happening, I mean, you kind of said, how does this thing even know where to go and get to where it's going to? So it's very much involved, we think, in the neuroinflammatory process. And so you have macrophages, you have Schwann cells. That Schwann cells are sort of the immune cells or the macrophages of the nerves. And when there's damage, of course, they help with normal conduction of nerve signaling, the Schwann cells.
It seems to be not only with these Schwann cells and macrophages, but also some of these other proteins. That's the problem, is that in the body, rarely do you have a structure or a compound, hormone, whatever, that does just one thing, right?
Yeah, no, absolutely.
Yeah. I didn't mean to interrupt, but that seems if I were to put myself in your shoes, I'm already getting a headache thinking like, all right, well, how do we isolate what's exactly going on? Yeah.
So what we think, hypothesis-wise at the moment, what we think is going on is that you have these neuroinflammatory factors. We might have cytokines and other types of normal inflammatory mediators that are being elevated because of the damaged tissue. But we also think that there are Schwann cells that are infiltrating and gathering around that damaged site to try and improve whatever is going on.
And this is in the periphery.
And this is in the periphery, yes.
So meaning arms, legs, sorry, for anyone that just keeping up. We kind of talk about, at least with regard to the nervous system, the central nervous system being the brain and the spinal cord, and then the periphery being a slightly different structure of nerve cells that exist out in the body. So
that's right. Yeah. And so essentially all the strings that come off of the central spinal cord, that's the peripheral nervous system, for lack of a better term. And that what we think is happening, those cells, Schwann cells, are somehow being activated to express that chaperone protein even at greater concentrations at its cell surface than normally you would see. And so because of that, we can take an advantage of that increased protein level with a compound that's very much very selectively targeting that protein. And we got very lucky from an early standpoint in our design and synthesis that we found some of the most selective molecules for this protein in the world. And I mentioned before that there's a lot of compounds that interact with this protein, this sigma receptor. And in fact, there's an old joke among chemists that we use the Sigma Aldrich catalog to order many of our chemicals. And the joke was that you could pretty much buy anything out of the Sigma catalog and it would bind to this protein.
Okay.
And that's where the name came from. So it's the Sigma receptor.
All right.
That's not the true story of the protein, just kind of a fun chemistry joke.
I like it. Yeah.
But what we do know is that many compounds bind, including many clinically used drugs. So lots of centrally used drugs like antipsychotics, antidepressants. There's a role of this protein presumably in those therapeutic areas as well, including neurodegenerative diseases such as Alzheimer's disease, Parkinson's disease, Huntington's. So there's lots of potential applications for molecules in this area. We've been really focused on pain because we're at a point in society and in the world where we really need some alternatives to opioids to try to treat serious and chronic pain, and try and get away from things that might have side effects like the opioids do. So that's
is that what, and we kind of jumped into it pretty heavy. Is that what got you into? So you're a pharmacist.
Yes.
Is that correct? Am I correct in saying? But also a medicinal chemist.
right.
So is that where the drug development portion comes in, or?
Yeah, pretty much. That's I like to call medicinal chemistry drug architecture.
Okay.
I think it's a more descriptive term of what medicinal chemistry really is we're building, just like you would go build a house with specific rooms that you want and specific features, we're building chemicals from simple starting chemical materials, and we elaborate those with certain functionalities and features that we want to have in order to hopefully interact with the target that we're interested in. And so I went to pharmacy school, got into pharmacy because my father's a pharmacist, have the history in my blood, so to speak. Really was interested in following his career path. He was a retail executive, and I thought that would just be a neat way. And as a kid, he worked all the time, but he traveled all the time, and that really appealed to me as something. But I think the most appealing part of it was that everybody that worked for him, and he had hundreds of pharmacists that worked for him, everybody that I ran into just
Seemed to like what they were doing.
Loved what they were doing,
Yeah.
and loved that they were working for my father, and just mentioned what a great person he was. And so he sort of led me on those life examples, if you will, as to what I could do, what I want to aspire to be. Interestingly, my mother was a comprehensive high school science teacher, and so the education side of me was there too from early on.
And if I may ask, it's a bit personal, but do you still have your parents?
Yes.
Okay,
yes.
so they got to see from a genetic level all the way to the professional level, the blending of both of them in how you turned out.
Yeah.
That's really cool.
I think they were pretty happy when I didn't pick one over the other. So.
Right.
But it's turned out really well, and I went to pharmacy school at Ohio Northern University, which is a small private university in Northwest Ohio. We talked a little bit about that earlier today, and from there I actually met a faculty member that was teaching medicinal chemistry, which is a course that pharmacy students have to take. It's basically the chemistry of drugs and understanding how drugs and their shape and their particular makeup of atoms interact with the particular targets that are going to be therapeutically relevant. And so obviously from there you go to pharmacology and you learn the detail of the signaling that happens when that interaction takes place. And then you move past that into the therapeutic aspects and understanding doses and potencies and all those other types of areas. And so I got a full picture of drug discovery through development, through marketing, post-marketing studies, everything that was there in pharmacy school. I had an experience to work in a research lab while I was in school, in a medicinal chemistry lab, and just loved it. And that mentor, Dr. Stephen Cutler, he's now the interim provost at the University of South Carolina, but he was the driving force for me to really think about going and pursuing a PhD.
So initially, that wasn't the plan. You were still on the I want to be like Dad track.
Yeah.
Okay.
Totally never the plan. And in fact, it was so much never the plan that when I went and he had set up a summer internship for me at the University of Georgia College of Pharmacy, which is where I ended up doing my PhD. But I went down there for the summer thinking this is just a summer experience. It's cool. Ohio Northern's a small university of about 3,500 students. Georgia,
big difference from UGA.
Georgia's a big place, right?
Yeah.
What I called a real college, a real university experience. And I thought, hey, this will be fun. And the music scene was good and all of that. So I went down there for the summer, really loved it, really loved what I was doing and the chemistry aspects. But, I packed my bags up to go back and finish pharmacy school and didn't really think twice about it. The chair of the department at the time at Georgia, Jim Stewart, who's now passed away, and who ended up being a huge influence on me in my career, he actually called my house back in the days before cell phones, right? So he called the house, and my mother said, "There's a gentleman here from the University of Georgia on the phone." And so I went and talked to him, and he said, "Why didn't you apply for graduate school?" I said, "I'm not going to graduate school." And he said, "Well, we have a spot for you. We were impressed with you over the summer. We'd really like to see you come and pursue a PhD." And I said, "Well, that really wasn't what I wanted to do." And so interestingly enough, though, in 15 minutes, I hung up the phone and I was signing up for the GRE and headed to graduate school.
Just like that.
Just like that.
He must have had a good pitch then.
I think it's interesting because it's amazing how one little thing in your life, 5 minutes to 10 minutes, can completely change your pathway.
Well, and I don't know. So for me also, when I came to graduate school, it was to get a master's degree. An opportunity at that point, I was teaching high school, and so I was looking for a master's. So I went. Obviously, it's here at University of Florida. And, well, maybe not, obviously. And so I went on the webpage, and I'm a first generation college student, so there's a lot about this process that I didn't know. I didn't know what I didn't know when it came to that. I was at that level. This is even after getting my bachelor's degree, and it was the same kind of thing. I sat down with Dr. Chris Janelle, actually, and he's still here. This is up in the College of Health and Human Performance. And I said, hey, I'd like to get this master's degree in human performance, and I'm interested in taking some classes from you. And this guy, a phenomenal researcher, and he's in performance psychology, and just outstanding, a brilliant guy. And he says, well, I really couldn't do that right now. I've just recently taken on a graduate student, which actually ended up being one of my best friends from grad school later. I hadn't met him yet. But he says, I really wouldn't be able to give you the time. But if you could wait a year, I'd love to have you back as a doctoral student. And I said, no, I'm just looking for a master's.
Right.
Well, I ended up back anyway. I probably could have cut the master's out of the equation. But yeah, it was the same kind of thing, where I guess the reason why I tell this story is when you got on the phone, and you said it was Jim Stewart that had called. So when you get on the phone with Jim Stewart, and he started telling you about why you should do this, did you really know what a PhD entailed at that point?
No, and in fact, some of the decisions that I've made in my life, I didn't know what I was getting into when I got into it.
Till it was too late.
That certainly was one of them. No, I didn't know. I knew pharmacy. I'd worked in a pharmacy through pharmacy school. I saw what my father had done. So I finished pharmacy school. I actually moved to Georgia, took my licensing exam in Georgia, and started practicing as a retail pharmacist at Publix supermarkets, which is all well and known in Florida, of course.
You can't do that in Ohio. You can't do that close to home or in Pittsburgh.
But in Georgia, they were just entering into the Atlanta market. And so Publix was very quiet about their pharmacy. That was a shopper's convenience. It turned out to be an incredible opportunity for me to work as a pharmacist and still be in graduate school because I could work on the weekends. And because there was not much advertising of the pharmacy and people didn't really even know Publix very well, I spent most of my weekends earning money studying. So
that's a great deal.
It worked out really, really well. And then I learned that through interaction with patients, customers, however you want to call it, at the pharmacy, I would spend too much time explaining the drug to them in terms of all the cool things about the drug and the pharmacology, and they would end up saying, "Well, do I take it with food or not?" That's really all.
That's really all they wanted to know. Yeah,
and so that's what sort of drove me to really decide that academia is probably where I ought to be, and I could have more influence on patient success by training other pharmacists.
So let me ask you, and I want to bring in a little bit more of what I'm certain some of our audience probably thinks when we hear medicinal chemist, drug development, drugs just in general. There's been a very big public sway recently, and we see this with opioids, obviously, rightly so.
Yeah.
Still have an ongoing serious issue with that, which we'll talk about how you're addressing that later. But just in general, there's a large segment of the population that says, well, if I look at a bottle and I can't pronounce this word, then I'm not putting it in my body. And it seems that that there's something lost in translation somewhere. When you're talking, for example, about some of these molecules and how you learned the components of a drug and how then it then interacts with the biological components of the body to elicit a response. When you boil it down to that level, if you could maybe just, and I say this literally, not you right now, but if you could educate people that, well, pretty much everything has a scientific name, and I'm certain that there are compounds in pretty much anything you eat, fruits, vegetables, anything, that you can't pronounce. And we just call them something else. And if you break it down to a certain level, that this is all that's happening. Not to say that there's not a nefarious element, and there's plenty of things in big pharma and whatnot that probably are justified. But at the end of the day, it probably seems to me that to take that same outlook on all of pharmacy, to somehow change from showing up at your dad's pharmacy or whatnot and saying, here's my prescription, and getting your bag of whatever that'll help your blood pressure or clear up your eczema, whatever the case may be, to this, I'm not taking any of this. There's something lost in translation there. So how do you rectify that as you're going through your career, and is that something that's played on your mind at all?
I'm laughing because my father was not one to take medications until he was really in the position to have to take medications. And I sort of inherited that thought as well. And he told me one time, drugs are to sell, not to take. And I was like, this is a strange perspective from a pharmacist, right? But yeah, I think there's that sort of mentality in a lot of the population as well. If you don't need to take something, then I'm not going to take anything that's foreign to my body. But certainly your point about not being able to pronounce things, I laugh all the time because we pick up the box of cereal or the box of ice cream that you're scooping, and you look on there and you recognize the first few ingredients, right? Milk, sugar, whatever it is, and then you get into things like xanthan gum and initials. They don't even put the whole chemical word on there.
Right.
And they're there to stabilize and prevent oxidation and spoilage of that food or whatever it is. But yeah, almost every food product we buy in the grocery store, unless you're buying a natural raw food, has some sort of supplemental chemical in it to help it prolong its shelf life, essentially.
Well, and even then, I would, you talk about raw foods. There are still, there's still compounds in foods that, beyond just cellulose, that flavonoids and all kinds of things that if you really boiled it down to what's in there, people would still run into that same roadblock.
Right.
We just have more common names for the combinations.
Right,
of these
and we really don't think about it. And if you think about any of the foods that are being consumed, they've been there for a historical period of time, and there's nothing with an issue of taking that because, well, look, everybody's been taking this, and this is what we do to survive. But yeah, if you start to think about it from a chemical perspective, I mean, man, there's all kind of things going on in there, and that's one thing that really drew me into natural products research, as well as doing the drug design from building a chemical from scratch, essentially, that we talked about with medicinal chemistry. But then there's the natural products chemistry part of it. The old term for that was pharmacognosy.
Pharmacognosy.
Yeah,
okay.
And so we don't hear that term very much anymore. We hear natural products chemistry. But I always believe that on the earth there was a balance, and if there's a disease that's been created in nature, there should be a cure that's equally out there in nature. And I've had that sort of thought in my brain since the time I was a kid. I remember using that exact same scenario when I went to interview for pharmacy schools. And we think about it, most of our original medicines were really based on plants and plant-based medicines. And we talked about opioids, and certainly, and most people probably don't know this, but the opioids are still isolated from the plant. And then they're modified into a pharmaceutical preparation. Sometimes that involves chemistry to manipulate those molecules into the molecules that are actually prescribed. But morphine itself and codeine itself still come directly out of the opium poppy plant that are grown in various parts of the world.
And it's not like they're grown to make these drugs or whatnot. They've been used in cultures for quite some time.
Yeah, for thousands of years before Christ, actually. Yeah. So since the earliest recordings of history, we know about the use of opium. We know about the use of cannabis. So some of these things that have been with history for a very long time that have gone into misuse, gone into bad spots politically and otherwise. But there's good from those plants. Obviously, we still use opioids as our mainstay of the best and most potent pain relievers we have. And they can be good if they're used in the right ways and in moderation.
Well, I want to ask about that. So from your standpoint as a chemist, there's, and particularly as a medicinal chemist, so we hear a lot about opioid receptors. And this seems to, in a way, circle back to what you had talked about with the balance in nature. So the opium poppy has compounds in it that we, as an organism, seem to be prepared to metabolize or to take in, and we already have, when we say endogenous receptors, these are things that are already within our body. So we're prepared to interact with those chemicals already.
Right.
But it seems as if there's the root of the issue is, like you said, misuse or abuse. But how are you looking at the fact that we have these receptors, and if those receptors are activated and bind to opioids, are there other things out there that maybe don't have the side effects? Because it seems like that's the major issue is with opioids. Let's say just with this pandemic, you take these and there are side effects. And one of the side effects is the fact that they're addicting, and then you have long-term side effects that are aside from the addiction.
Right.
So what are some solutions?
Well, I don't know that there's actual solutions yet. I think we've been working on those for decades and longer than you and I have been alive. But certainly there's some promise out there with other plants. And I mean, before we talk about that specifically, I think it's important to understand when we talk about plant-based medicines or plant-derived medicines, what we've done is we've taken the opium poppy, which is a system, just like our human beings are systems. And
I just real quick, hold that thought just for anybody to catch up. We have building blocks. Everybody understands cells. So cells combine to form tissues into organs into systems into organisms. So the plants function much of the same way, you're saying?
Mostly, yeah. And of course, they don't have a nervous system, and they don't have, but they do communicate with each other, interestingly enough. And that's a whole nother discussion topic. But these plants have grown and evolved into a balance within themselves, just like a healthy human being has grown into a balance with themselves. And yes, we do have endogenous opiates, the endorphins, and we hear about those, and we hear about people that exercise to the point where they get high.
Like a runner's high.
Because you go through the pain part of it, and your body's natural response is to release these pain-relieving peptides. They're there for protection of us. They're there for, sort of a reason. There's a long history of the evolution of the receptors. There's at least 3 different types of opioid receptors that are traditionally recognized. And I think it's fascinating that we don't think about the other systems that are counterbalancing those in our bodies. So when we have a whole intact system, we don't generally get tolerance or constipation or addiction. Well, you could argue that with the runners and the athletes to our own endogenous substances. We don't get respiratory depression. These are the side effects that we hear about from opiates, purified opiates away from the poppy plant. Not to say that the poppy plant can't cause all these problems in the whole opium extract that you would think of as well. But we have endogenously in our bodies, we have other systems and other peptides and hormones that counteract the effect of our endorphins as well. And so some of our research in getting to how can we address some of the opioid problem, some of our research is looking at some of these other systems that can potentially counteract those effects that we see, the side effects.
Do you think so? There are other. So you mentioned our endogenous system and how there's a balance, and it seems like that's the case with most physiological processes. Is there's something that upregulates and something that downregulates, and if you have everything working the right way, then you get just what you need. And you mentioned, say, with opium, for example, these are isolated compounds out of this plant.
Right.
So are you saying that, and I'm going to lead you a little bit of a field here maybe, but is it possible that there are other compounds that you could either add to that isolated compound that would, you mentioned respiratory depression, for example, big issue, right? You take too many opioids, your respiratory rate slows and you can't control it well. If there's any reason for upward deflection, you have to breathe more, you need more oxygen, your body doesn't respond to that. Is there something, are you saying that there may be something that you could add to this isolate, or maybe that if we didn't isolate so much of it and looked at maybe more whole plant things, that there may be something that would provide a balance?
Yeah, so I think the best example of this right now that most people could probably relate to is cannabis. And it is kind of changing direction a little bit, but cannabis is really a plant with hundreds of chemicals in it, like most plants are. You hear people talk about what's an entourage effect. In other words, we need all the chemicals present, not just THC, which is the main psychoactive ingredient, pulled out, or CBD. We hear a lot about CBD products, CBD being isolated out by itself. So there's a belief that you need that whole plant balanced with all of its chemicals to really have the full effect that you're going after. And I guess what I'm getting at, and I've always described natural products in sort of this way, is that you have a symphony orchestra in the plant, and you've got all these instruments playing at the same time, or some are really quiet and some are very, very loud. And what we're doing when we isolate those molecules is we pull one of those instruments out and we listen to it full blast. And we're getting everything that we can from it. We don't understand, if something else was in combination with it, or what else would be happening if it was intact in its plant, right?
I love that. That's a fantastic analogy.
So, yeah, it's one of my favorite ways to try and explain this, because obviously if you just listen to a drum set, it can be headache-inducing to some people. But if you listen to it with the bass and the guitar and the lead vocalist and the keyboards, all of a sudden you've got this really cool music, right? So that's kind of where we get to. And then we can think of our bodies the same way. I mean, we've got all these endogenous chemicals and hormones and neurotransmitters going all the time. And sometimes some need to be louder. Sometimes some need to be quieter. And it's just that balance of everything intact. And so, I'm
stealing that for the record. I like it, because you could go even farther and say, or further for anybody that's nitpicking my grammar. You go even further and say, we don't even know at any given point if you isolate something. Let's say you take the viola out.
Right.
This is for all of you viola players out there. Got to throw a viola joke in, but the viola's in here. We get the melody, right?
Right.
So you pull the viola out, and it not only is it not the whole thing, but it's maybe not even I hate to say it, maybe it's not even the important part, right? It doesn't have the melody at that point. Now, and in some cases, if you take an entire compound, or an organism, I should say, that has all of these plant compounds and whatnot, and you get tell me the entourage.
Right.
So this entourage effect, there may be certain compounds of that entourage that are more important in certain parts of the body or in certain situations or whatever, even certain conditions, when others maybe play a larger role at other times.
Correct.
I'm totally stealing your analogy.
Yeah.
I love that.
No,
I
I think it's great, because you can even talk about different parts in the same section, right?
Right.
So
it's fantastic.
There's all kind of things to this, and the different parts in the same section will be different locations in the body where those chemicals are going to interact. Right?
Well, I think we can agree. You always need more cowbell, though.
Yeah,
always more
cowbell. Never a doubt. But I think it's really important, given the other area that we're working on. So I sort of hinted to working on other neurotransmitters in our body. So there's the endorphins that are endogenous opioids that will help us when there's pain or some sort of trauma to our system, so that we don't totally lose it. But at the same time that those endorphins are released, other chemicals are released as countermeasures, if you will, to make sure that our body doesn't overreact or become sensitized or desensitized to our own protective mechanisms. And so we've started to target some of those peptides, and by making small molecules, again, going back to that medicinal chemistry drug architecture design of specifically trying to have elements of these endogenous molecules contained within a molecule that we've designed as a potential drug molecule down the road to block some of those countermeasure that are released when we use an exogenous substance. So I got to back up a second there, because
we've thrown a lot out on the table. We've already determined that you're coming back, so we don't have to get everything in one episode.
So that part is really interesting. If we start to take opioid like morphine or oxycodone or hydrocodone, what happens is our body shuts down the endogenous production of our endorphins, because the body says, hey, we've got this system activated. We can back off and put resources into other things that we need to be doing to take care of this whole being. And so they shut down endogenous production of opioid, endorphins, and those and the like, because we're taking this as an outside medication. The body believes that that system is still being activated by the endogenous or the normal. It's being tricked in some aspects, that it's being activated by the normal physiological mechanism that would be there, that endorphin. And so even though it's not, and we're not producing the endorphins, the body then still is releasing these countermeasures. And so these countermeasures are designed to sort of protect us. The problem becomes when you take the opioid away, the exogenous compound, the morphine or the oxycodone, you take that away, the body has a period of time where it has to readjust and turn the system back on.
Right.
And synthesize our own endorphins. And when that happens, we go through what's called withdrawal because we don't have that opioid system engaged.
Do the countermeasures, so you're talking about the elevated countermeasures because you're supplying an exogenous opioid. When you take that away, do you see, now you said your body has to turn back, the system back on to produce the endorphins and whatnot. Do you see a decrease in the countermeasures immediately, or does that take a while?
No, that takes a while to shut down because that system's ramped up and just really going at it.
Right.
And so what happens is some of those countermeasures produce a phenomenon called hyperalgesia, which makes us more sensitive to pain. So, bumping your hand on the table at a normal situation is not painful,
right?
But in this case, it could be very painful. That's what hyperalgesia is, where it's not normally painful, but it becomes incredibly painful. There's a phenomenon called opioid-induced hyperalgesia, and that's what we see a lot of times. Patients will finish their opioid therapy. Say you had a molar extracted or some broken bone and you were prescribed opioids for a certain number of days. That exogenous treatment, those prescription drugs, will shut down that endogenous, like we just said. But these countermeasures are still going. And you withdraw that prescription drug, and all of a sudden you have these countermeasures taking over. So that's where this hyperalgesia can come into play. And then it starts this cycle of, oh, doc, I still am in pain. I need treatment, when in reality, the inflammation and everything that would indicate you should be in pain is gone.
Yeah.
Right. But it starts this sort of vicious cycle, and of becoming physically dependent, which then can become, psychologically dependent, and in some of the other problems where a typical normal use of an opioid can turn into a habitual problem just because of the physiological mechanisms. And what we're doing is really creating a disease state within our bodies, and then eventually that ends up becoming the disease of addiction.
Right.
And we don't talk about these two things very often when we talk about pain and we talk about addiction. They're usually dealt with very separately. And part of the things that we've been interested in for years is trying to figure out where is that sort of intersection point, and when does someone that's perfectly fine and being treated with a painkiller sort of cross that threshold and become physically dependent.
Because there are a lot
addicted.
of people who, I mean, I've discussed this on the podcast before. I had a knee surgery, and I was on painkillers for a time after that, a brief time, because they're pretty tight with that now, even in Florida. But I had no issue with that I noticed with any kind of withdrawal or any kind of addiction or anything like that. So people do go through this process very normally. Is there something that may predispose people to? So, I mean, obviously there's the psychological thought of the psychological disease of addiction, but from this standpoint.
Yeah, I believe obviously there's probably genetic components. There's certainly things that we're learning about in terms of metabolism and drug metabolism, and there's a lot of work going on here at University of Florida within pharmacogenomics, particularly in the College of Pharmacy, and looking at drug metabolism and what rate individuals are metabolizing drugs. So some people are very poor metabolizers of certain drugs. Some people are moderate or normal
Right.
metabolizers, and some people are ultra super sensitive metabolizers. And to what extent those genetic makeups link to some of the other issues is still not well understood. It's definitely considered probably a component. There's a genetic component there. But there's no smoking gun link that says if you have this, you're going to become this. And so we should avoid these medications in those individuals. I mean, that's the goal of where we want to get to, and we want to get to a real good place for personalized medicine, particularly in pain treatment, for individuals to respond the best way. I know speaking a lot with Roger Fillingham in the Price Institute, it's one of the things is phenotyping pain and trying to figure out, what level of pain deserves this drug or that drug, and where can we get away with, the least, potent or the least powerful drug, but to come with a beneficial outcome for the patient.
Well, that's got to be difficult too from a patient care standpoint, because when you're in pain, normally with pretty much anything you do, you don't want to go out swatting flies with sledgehammers. Pain, on the other hand, when somebody's in pain, they want it gone, they want it gone all the way, and they want it gone right now. So if you can give me this, even if it's not necessary for this level, I want it. So I think there's a little bit of an education chasm there, because people don't understand that, well, actually, you could take this over-the-counter drug, and if you take it at this frequency, this will do the exact same, and without all the side effects and all that, but you have to kind of triage those levels of pain.
Right, and I think that's one of the problems is you described it well with the hammer or the sledgehammer, really, because that's what our opiates are. I mean, they're incredibly powerful and very effective at relieving the pain, but that's sadly one of the only tools we have. We have that, and then we have sort of the non-steroidal anti-inflammatory drugs, which I call the rubber mallets of the world, that they're still going to do the job, but if it's a really sharp, serious pain, it's not going to be able to handle it.
Right.
So you've got basically that lane of or this chasm in between, where we've got lots of opportunities to try and find new types of treatments and new ways to handle this. And so that's a lot of things that we're trying to do. That's a lot of things that the National Institutes of Health is trying to do by fostering, programs and putting grant monies out on the table to find non-opiate, but just as effective as opioids, but non-opioid painkillers.
Well, and I know, so to have you on today, you just recently, and congratulations on this, but recently submitted a grant.
Yeah.
And anybody in academia knows that when you get right down to that deadline, everything else needs to be put on hold, and you gotta do that. So congratulations on getting that sent off.
Yeah, thanks.
But I think that, because we didn't even touch on, and we're kind of running short on time, if I could be honest. This is fascinating. I'm sure everybody listening along would agree. But you're doing some work, you had mentioned, in collaboration, looking at cannabis and also at kratom, depending on where in the world, you help me out with this, depending on where in the world you are, it's pronounced a couple different ways.
Yeah, well, in the U.S., it's mostly kratom.
Okay.
In Southeast Asia, where it originates from, it's kratom or kratom.
But it's also a plant, correct?
Yes.
Okay, so there, aside from cannabis, right now the hot button is cannabis, and you had mentioned CBD, and some of my other guests have discussed that. I'm currently conducting some research as well, using CBD, but the entire spectrum, whether it's hemp or cannabis, but it's there are plenty of plants around the world that have been used for therapeutic or medicinal purposes that are now starting to be looked at from an empirical perspective and saying, okay, what's going on here, and can we run these through some randomized trials and see what effects there are. You're working on that with kratom right now, and have been for a while. You're one of the experts in this.
Yeah.
And so I think what we need to do is leave that almost as a cliffhanger and have you back, maybe as soon as possible, for a part 2, maybe before we all leave for the holiday if we can. And
that'd be
because I'd really love to hone in on just those two elements, the kratom and cannabis, and talk about how, now that we've laid the foundation, of some of the issues with pain relief and therapeutics and maybe even prevention that medicinal chemistry can hope to address. We'll talk a little bit about how you're trying to do that.
Yeah, and I think just to even make the cliffhanger more.
Yeah, hang that carrot out there. Do
more
it.
of the Friday afternoon cliffhanger, from the soap opera days. What we're learning about kratom is really fascinating. So there's been a huge focus, and most of that focus has been on the opioid activity of the plant.
Mm-hmm.
But what we've learned is it has activities at many other systems, including serotonin systems, adrenergic systems, which is our fight or flight systems, and serotonin, which is involved in mood disorders.
Sure.
And so a lot of the anecdotal claims that are being made by people using kratom products are starting to shed light on the mechanistic studies that we're starting to shed light on some of the reasons why they're there. So it'll be fun to talk about that. And again, it'll be fun to talk about this analogy of listening to one instrument at a time versus what do we do with the whole orchestra.
And so just to kind of again round this out a little bit, is kratom the new kid on the block, or has it been used culturally for as long as something like cannabis or opium poppy has?
Potentially as long. We just don't have the written records of it. But it's a Southeast Asian, particularly Thailand, Malaysia area where it sort of started, the border where peninsular Malaysia meets Thailand. It's been used for hundreds of years, we know that, particularly by laborers to help stimulate them work harder. Not too different from what we've heard about cocaine's use in South America. And if it's chewed and if it's utilized in a certain way, it has certain effects. Of course, if we isolate cocaine out of that plant, we know what issues there are with that. Although cocaine is still used as a pharmaceutical. And I didn't mean to get off on that.
This is good because everybody's taking notes here and they're like, I'll get the emails. Oh yeah, you got have them back on.
This is interesting because the use of kratom for centuries that we know of in Southeast Asia has pretty much been under the radar, and we'll get into even more depth of that next time. But it's pretty new in the Western world. And, of course, anything that's new and has been tied to opioid starts to get experimented with and misused and abused and mistreated. And we start to see problems arising with the use. And so we started
And that's already happening here in the U.S.?
We started seeing harm in the U.S., even in Europe, with ingestion of kratom leaf material, plant leaf material. But most all of the cases were involving co-ingestion with other drugs or alcohol or substances to try to see if they could boost the effects of this. So it's unfortunately been labeled because of a subset of the population, and a very small subset of the population that has gone and experimented with things that.
So it's like the meme says, though. And that's why we can't have nice things, right?
Yeah, exactly.
There's always somebody that's going to misuse or abuse or overuse,
but we believe there's somewhere in the neighborhood of 15 million people using kratom in the United States alone. So just based on internet.
And is that
sales,
from that's a recreational kind of usage you're saying?
No, that would be for therapeutic benefit actually. So most of the individuals that have been interviewed and talk about kratom do it from a standpoint of it has replaced my opioids. I now have energy, whereas when I was on opioids, I was on the couch. I was disconnected from my family. That became the focus of my life. Whereas kratom has given me the opportunity to re-engage, get my family back, have my energy, but not have my pain. It also seems to reduce anxiety, and so anxiety is a huge element of pain. And then it seems to lift the mood, which I already mentioned a little bit. And so you see people using it for different purposes, either to be off opioids, or to elevate their mood or to gain their energy. And so there's all kinds of ways to go with studying this and trying to understand what components of that orchestra are responsible for the different pieces and parts of the therapeutic aspects is really what we're trying to do. And so I'd love to come back and talk more about that.
Sounds like we've got plenty to talk about.
And see where we're going. But I truly believe that it'll probably be the next medical marijuana if we can keep it from getting scheduled and banned.
Well, and that's why the research is so important.
Right.
Well, thank you so much for coming on. Now, do you have a lab website or that anybody that's interested in your work and to learn more about this? Because I think we need to put as much real information, good information out there as we can.
We actually have and I'll make sure we talk about this the next time, but we can at least put it out there. We have a kratom resources website where we keep as much up-to-date scientific information there as possible. It's non-biased in any direction. It's just pure factual information about what we know. I don't have a lab site per se. I also do direct the Clinical and Translational Sciences Institute's Translational Drug Development Core, where we work on taking drug molecules and making them into potential drug-like molecules that would go into clinical trials. We do have a website for that part of our work. And then I can be reached by email, which is pretty much publicly available everywhere, but it's C McCurdy or CMCCURDY at UFL.edu. And so always entertaining emails from many kratom users. I'm not a physician, so I just want to make it clear that I can't, tell you how to take it or recommend what product to take or anything like that, but I'm happy to answer questions from a more science-based perspective. So.
Well, I'm really looking forward to, so add me to the list of all the listeners, but I'm really looking forward to the next time. We should probably do it sooner than later, but in the meantime, thank you so much for coming on. I thoroughly enjoyed this. Some episodes go by faster than others, and this one just flew by. There's so much to...
Well, thank you for having me. It's been fun, and one thing that I'm not short on is words. So
well, maybe that's why Roger Fillingham said the two of us should talk then, because I'm the same way. Maybe he just wanted somebody that would make me sit back and listen for a change.
Thank you for joining this episode of The Price of Pain. Opinions expressed on this podcast are solely those of the host and guests, and not representative of the University of Florida or parent institutions of our guests, unless specifically stated. You can find more information about Price on the World Wide Web at price.ctsi.ufl.edu. And keep up with our researchers on social media by searching Facebook for UF Price, by following @UF_Pain on Twitter, and Price of Pain Podcast, all one word, on Instagram.